and I'm looking for an x, well, no matter what A is, x equals 0 would be a solution. So I could just say all the m's are equal to 0. And that would not be a very satisfying solution. So the question is, what's the best way to solve this? So as I said, this is a homogeneous set of equations. Now, when you have a homogeneous set, like am equals 0, and let's suppose you have a lot of equations, well, clearly, what you'd like to do is you want to place some constraint on m, because I don't want to let it be 0, but then given that constraint, I want to find something that sort of computes the smallest square value of a times m, and that's what's written here. So I'm going to try to minimize the magnitude of am. Now, m is only valid up to a scale, and we know that for a couple of reasons, right? One is you can just take a look at these equations here, right? Since everything's equal to 0, I could just scale m, or I can go all the way back to my perspective equations, because clearly if I scale all those m's by a value, when I go from the homogeneous to the non-homogeneous, when I divide uw by w, that scale factor will go away. So m is only defined up to a scale, that matrix m, all the little m's. So since it's defined only up to a scale, let's just assume it's going to be a unit vector. Okay, so its magnitude is going to be length 1. And the question is, what's the best unit vector m to minimize the magnitude of am? I'm going to tell you the solution here, and then I'm going to show you that it's the solution. And some of you will have seen this before, and some of you won't. The solution to minimizing am, the magnitude, when m is a unit vector, is, as you all know, I'm sure, because you studied this all the time, you want to take the eigenvector of A transpose A that has the smallest eigenvalue. Of course, you say, I know that all the time. I'll show it to you in a minute. And by the way, this only works when you have 6 or more points, and that should make sense, right? How many degrees of freedom are there in M? There's 11, because there's 12, but only up to a scale. Well, I get 2 equations per point, so I'm going to need at least 6 points. But of course, this thing works a lot better the more points you have. All right, so let's go through the solution. So here I've written as if I only had 2 points, point 1 and point n, with a whole bunch of points in the middle. Okay, so I've got the matrix A times m equals 0. How big is the matrix A? Well, it's 12 across, right, because there are 12 m's. And how many rows does it have? Well, it has 2 times n, where n is the number of points. So it's a 2n by 12 matrix. M is just an m by 1 vector, and here's the 0 vector of length 2n. Okay? So now let's talk about solving that. One step at a time here. All right, so here's our goal, right? We said we want a unit vector that minimizes am, a unit vector for m that minimizes am. So let's do what's called a singular value decomposition, and I'm going to assume that you've seen that before, at least someplace, but the idea is that any matrix can be decomposed into this UD V transpose format where V is a real orthogonal matrix. So in our case, it would probably be a 12 by 12. U is going to be a much bigger matrix. It says orthogonal, but I should be more precise. Each column is orthogonal to each other, so that would be, in this case, a 2n by 12. And most importantly, D is a diagonal matrix, so it only has values in the diagonal, and it is customary to write it as in decreasing order of absolute value, so from the biggest D to the smallest, all right? So we're going to write A is equal to U dV transpose. So minimizing AM is the same thing as minimizing U dV transpose M. Got it? So far, nothing significant other than you have to use your singular value decomposition code from MATLAB. Here comes the first little bit tricky part. That is that the magnitude of U dV transpose M is equal to the magnitude of just dV transpose M. Why? Well, these are just unit vectors, right? The U's and V also, for that matter, are made up of orthogonal unit vectors. So multiplying them doesn't change the magnitude of the matrix. And that's why these magnitudes are the same. And it's also why the magnitude of M is equal to the magnitude of V transpose M. For those of you who think about such things, V in this particular case is a orthogonal, in this case 12 by 12 matrix. You can think of it as like a rotation matrix. So when you rotate a vector, you don't change its magnitude. So the magnitude of M is the same as the magnitude of V transpose M. So that means instead of minimizing U dV transpose M, we can just minimize dV transpose M. subject to, instead of being subject to m equals 1, subject to v transpose m equals 1. Got it? Now you might ask, why are we doing that transformation?
Why are we doing that transformation?
Here's why. It's going to let us do some very cool substitution. So we're minimizing dv transpose m. Let's do a substitution of y equals v transpose m. So now we're minimizing just dy subject to the magnitude of y equals 1, right? Because v transpose m is y, its magnitude has to be 1. Okay, so y is a unit vector. Why? Why not? No, never mind. Because it is, all right? But think about d times y, all right? dy right there. Remember, D is a diagonal matrix whose elements are in decreasing order. So what is the smallest that dy can be? When is it the minimum? Well, it's going to be a minimum when y puts all of its weight, remember y is a unit vector, just in that last element. All right? So the best y for minimizing dy, given that D is a decreasing ordered diagonal matrix, is just 0, 0, 0, 0, 0, 1. Okay, that's the y that minimizes dy. And since we defined y to be v transpose m, then m is equal to vy. Why? Well, remember I said that v is orthogonal? Right? So when v is orthogonal, its transpose is its inverse. So if y is equal to v transpose m, the inverse of that is just v, so m is equal to vy. So now we've solved for m in terms of y, but v and y, but remember, y is just 0, 0, 0, 0, all the way 0, 1. So that means that this equation just pulls out the last column in v. All right? Because if I take a matrix, all right, and I multiply it by some vector that's all zeros down to 1, that 1 just multiplies the last column. So I just pull out the last column.